Hi, everyone. I'm Swetha Salunke. I'm part of the AWS Amazon DynamoDB team. I run a product management group that takes care of a lot of developer experience pricing related features for Amazon DynamoDB. So this particular presentation, I wanted to walk through how exactly we think about event-driven serverless architecture with DynamoDB and some of the core functionalities that we built out that you can use for event-driven architecture and how the thought process came about for building these core properties of DynamoDB. So before we go into it, I just wanted to give an overview of DynamoDB for anyone who's new to DynamoDB or hasn't heard about it. So DynamoDB is our managed NoSQL database at AWS. Basically, what it means is we will provide you consistent performance at any scale, and you will not have to manage any instances. There is no downtime for any version upgrades of any sort, which makes it serverless. And this is used as a base for building event-driven architectures, be it a social media company that wanted to send you notifications for any changes in your network, for example, or if it is a company that wants to send you your rideshare information. Those are the kinds of things that are built on DynamoDB. So you can think about the scale that we need to handle. So when we talk about scale, what we mean is global locality. What does global locality mean? We actually have globally replicated data, which means you can have the same data written to two different regions, and that basically lets us give you consistent millisecond performance. So let's move on to the core functionality of DynamoDB that actually lets you build on top of it for event-driven architecture. So logs, one of the most basic concept of key distributed systems that allows you to build applications for correctness. And some of this might be very basic for all of you. Some of this might be something that you already know, but I think these are important concepts that you must keep in mind when you're building a large-scale event-driven distributed system. And to start a conversation, we are going to go back to a very primal concept of logs. And let's talk about logs. Logs in databases have been around and fundamental and have been around for a really long time. So you can think about this as first databases with spinning disks, where you commit a particular write and you wait for the acknowledgement. There is no actual index storage written at that time, which occurs in a random location on the disk. And this basically allowed the databases to increase throughput. So we're going to talk a little bit about elections, but in this case, the election is basically people voting for their most hated vegetable. So the contenders here are kale and cabbage. Let's just say, so an operation is a put for a vote for kale, and that goes from a transaction log to an actual table. Secondly, you put a vote for cabbage, and that goes eventually into the transaction log into the table itself. And, it's not just used for writing and speeding up your write throughput. It can also be used for crash recovery, specifically when a database wakes up. The first thing it's going to do is check, did I die in an inconsistent state? Meaning, did I die while I was trying to write a transaction into a table or between a transaction? And if it detects that that's what happened, what it's going to do is basically check about what information had already been materialized and where and what state of the transaction was I in the middle of processing. Was that transaction committed? And if so, it's going to continue onwards and it's going to get the database to the point where the transaction was committed. If the transaction was not committed, it's going to go and roll back to the previous set of transaction. And that's how it recovers quickly. Aside from crash recovery, the other fundamental operations that logs can serve is to build the first set of distributed databases. So for a second, let's say MySQL database with a lot of read replicas, that essentially you have a distributed database. And at the center of this distributed database, again, is a log. And specifically, what happens is that you've got a primary and a secondary. So here's what specifically happens. You've got a primary that is a thread for every single secondary, and that's trying to keep up with the primary itself. So on the secondary, there are two threads. One thread basically goes to the primary and says, hey, primary, please start sending me all the updates starting at this point. And all that thread is going to do is blindly write those logs locally on the secondary disk. There's a secondary thread which will basically use those logs and apply and materialize it locally, just like it would on the primary database. And with this, you've got the ability to have a primary and secondary application. You've got the ability to increase your rate of throughput in your distributed database to build something even as trivial and simple as primary, secondary replication here. So there's a few fundamental primitives that you must keep in mind. And the first and foremost is the ability to have these logs in an ordered semantic. And what do I mean by that? So imagine that you have a vote. You have 3 votes coming in for Kale. And then somebody says, well, this candidate is no longer running. So Kale is not in the running anymore. I'm doing the votes, and you want to delete all the votes that you've put in for this candidate. So in this scenario, the end state of the table is that there are no entries in the table at all. But now imagine the exact same example where the order is reversed. So let's say the delete happens first, and there's nothing there still to delete. And then now you go through and apply the insert. So in this scenario, the insert is happening after the delete, which means that the primary and secondary are now in consistent state, where your primary has no records, and the secondary is basically giving you the records that should not be there at all. So this could lead to all kinds of weird things that you're going to have to debug downstream. So the same thing applies with deduplication, right? Like duplication. A record can only occur in a log exactly once, and the same entry is found in the log multiple times. That again could lead to a different semantic on the secondaries and different semantic for downstream customers. So for those of you who are wondering, well, I don't use MySQL, I don't have to write, a distributed database that's doing the replication. The fact of the matter is these are the same primitives that have been around for the longest time, and you are going to get to apply them. So another key concept that we'll talk about is ordering. After ordering is checkpoint. And very specifically, if you go back to the days of doing crash recovery, as you are processing the log, you want to keep a pointer to how far you've processed down that log. So that if you crash and then wake back up, you can resume the delivery and processing from where you've left off rather than the beginning. For example, like we are talking right now with these slides acting as a checkpoint. And if I suddenly must go out and take a call, I can either start from the beginning and bore all of you with the initial slides with what I've already talked about, or I can start at the point where I left off, which is the checkpoint slide and checkpointing. When you're building a distributed system, log customers, you have multiple options and trade-offs that you make with checkpointing. You can checkpoint after every read or every message is processed, or you can checkpoint after every other message or after every end message and so on and so forth. Each one of these decisions have trade-offs. If you are checkpointing on every write or every message that's processed, you're creating a lot of write throughput. And you have to deal with this and the costs of this. But if you're checkpointing too infrequently, there may be more things that you must process if you have a crash. But it actually gets even more nuanced than that. So let's talk a little bit about what happens when you're processing a log. So imagine a scenario where you have processed 1, 2, and 3 events. 1, 2, and 3 have been processed, but your checkpoint is still at, I have processed 1. So even though you process 2 and 3, you're going to only have the checkpoint at 1. So you're going to repeat 2 and 3. Now, some of you might look at this and say it's not ordered. And I will say this is ordered. It's just ordered in a very nuanced way. So very specifically, if you look at it, the fact that you went from 3 to 2, it means you went back in time. But after there's a 2, there's also a 3, which means you actually go through the entire sequence. So for example, if there's 1, 2, 3, and 4, the next after 2 and 3, you will go to the next record. So you are finishing the entire sequence. So the primitive that guarantees you that you have here is that you process 3 after 2 always. So you're not skipping to 3, you're not missing out on the sequence, you are actually going through the entire sequence. Let's take a real world example of this, right? Let's say you have a ride sharing service, and you see the service that the car is constantly transmitting how far it is. I am 300 feet from your house, I'm 200 feet from my house, and I'm now at your house. So event 3 is I'm at your house. Now imagine if you didn't have the semantic for 1, 2, 3. What happened to the rest of the house? But again, you go back to, sorry, go ahead. Just a second. Yeah, but it's big up. So let me just try and
This meeting is being recorded.
Yes, I can hear you, James. Sorry about that. I think I just want to make sure I'm starting at the right point. What? Okay, that's the perfect time to stop, I guess. Let me just share my screen. So again, as I was talking about checkpointing, um, as I said, I could either start this entire presentation from the beginning or start at the point that the slide stopped, which is my checkpoint, essentially. So we were talking about like the specific example of a rideshare. So what you want in the case of the rideshare is that if the rideshare is at my door, if it came to 0 feet, and now it's 100 feet away, you're basically thinking that the rideshare has gone in the opposite direction, right? So how do we deal with it? This would be prevented if we checkpoint after every entry is processed. So what that guarantees is in the worst case, you will repeat yourself, which means it'll say 100 twice, or it'll say 0 feet twice. So you're still processing 3 for the second time. But before checkpointing 3, worst case scenario is what I'll have is 1, 2, 3, right? So in this scenario, I'll never go back in time, and I can continue making progress. So the worst case scenario is I'll get the update twice, but I'm not moving back in time. So this sort of checkpointing is very critical in this specific use case, but obviously there are multiple trade-offs. There is cost optimization, there is exactly what customer experience you want to provide for the customer in this case. So let's move from checkpointing to looking at a few trends that we see with DynamoDB and how customers are building and developing their applications. One of the trends that we are seeing is developers are building application to optimize for a global user base. And a lot of you also might have to deal with that. So what that means is essentially, let's take the example that you're building a gaming application. And what you're trying to do here is give the same experience to all users across the map, essentially. Let's say you're only working with the US audience, but you have a user that's playing in Portland and a user that's playing in New York. So you're trying to optimize that everyone gets the same experience, and technically that boils down to cross-region replication. What you're doing is whenever a write happens to your database, you want the data to exist on the other data center also. So to get to that, what you will do is dual writes. So you have a client which writes to the first region and then replicates it to the other region. Another trend we are seeing is protection against logical corruption. So DynamoDB, it provides durability guarantees, durability properties, which means that any write that comes in, it's physically durable across 2 data centers. And once it's durable, then only we acknowledge it back to the customer that the write actually happened. But still, what could happen is essentially the durability guarantees will not happen if your application goes rogue and deletes some of the items, or it doesn't prevent you against logical corruption. So you can have all the copies and replicas you want in the database. It's not going to protect you from a drop table, right? Or a bad deployment that just goes and starts corrupting the data because, again, the database is going to persist the drop table really well too. So to solve this problem, what you need to do is something like a point-in-time restore, where you can go to a specific point in time in your database and just apply the logs or undo whatever changes happened and correct your database state. Another trend that we are seeing with our customers and developers is that they want a production workload separate from the analytics workload. For example, they want to build something like an Elasticsearch cluster where they can enhance the query capabilities and keep it separate from the production application. Similarly, they want to build a Redis cache in front of the database that they can serve some of the queries from the Redis cache. And if not, a cache miss will happen and it'll go directly read from the DynamoDB table. In general, the key trend that we see is data is becoming larger and larger, and it's becoming untenable to just do these expensive queries across the entire database. So the selects and joins are becoming out of date if the scale is high enough, especially when people are trying to do aggregations and build leaderboards. And very specifically, if you think of the example, if you wanted, for instance, to keep track of how much data you are storing in an S3 bucket that has 10 billion files on it. You could have a nightly job that's going through and scanning the entire bucket and getting the size every single night. And every single night, you would know how much data has been stored in that S3 bucket. You can change the deletion, update every part. You can change the total size based on the old value and the new value, and give yourself a real-time metric. But again, that could be expensive for the use case that you're looking into. And in general, we are just seeing that people in real time want leaderboards and other systems. They don't want to wait for a query to run ad hoc and then get that information. They want it in real time, for example, with gamers. So that's the trend of event-driven architecture, where you're basically building your application without several applications where you just get the notifications. So you're not really building an aggregation system internally. This is based on each trigger that happens. So writing Lambda functions and corresponding to the taking actions, inserting to the table in the database and updating the state. So with every update, you update the state. So now let's go back to the first trend that we were talking about, which was basically a cross-region replication. I mentioned that you want the data closer to the user. So if you must do that problem without anything like a database, DynamoDB stream or anything of that sort, the way you would have to build this is your client does dual writes. So as the write happens, it goes to the first database, and from there, the client also has the logic to replicate it to the other database, which in this case, one is in Portland and one is in New York. Now again, if a distributed system and your application could crash right after inserting into your first database, now if that happens, then your two databases are not in sync. What you would do is you would write a sweeper that sweeps your first database and then make sure that the second databases are in sync, or whatever number of replicas you have are in sync. If something is missing in the first database, you would put that in the second database, and your logic that you've written in the application will be super complex, because what you're doing is you're adding more regions. If you're adding a third region, fourth region, you must go and change your application logic on the client side to make sure all the updates are going to all the replicas. It gets even worse, right? Like with the number of replicas and number of regions that you add. So imagine if you've added a new region and we've got a bunch of applications that are writing to 2 regions or 3 regions, and then you submit an update. Now, the new application must be writing to all 2 or 3 regions, but the old ones aren't, and it creates all kinds of uncertainty across the pair or the 3 regions that you have set up. So now, to solve like an obvious way, what you would do is you would solve the problem on the client side. And to solve the problems, ideally, you would have a queue that you basically like write to the queue, and the queue basically puts this data in all of the replicas that you need it to. If you have like a bursty traffic or traffic with peaks, and you want to absorb these spikes in your database, essentially, what you would do is create a certain provisioning throughput in case of DynamoDB. And once the writes increase, you put it in a queue if it exceeds the provision capacity. And then you do an asynchronous job, which is writing to the database, and which you'll use the same concept to write to multiple regions. So essentially what you're doing is a queue processor, which is listening to all the updates in your queue and replicating them across multiple regions. So in this case, if you keep adding regions, the logic doesn't really change as such. So your update is going to sit in the queue and get applied whenever it needs to get applied. So let's look at all of these scenarios that we talked about and what's the building block that's common between them. Now, if you must build in a point-in-time restore on top of DynamoDB streams or this changelog, what you're doing is you're just writing a processor, all the failure cases around, and what we've discussed around checkpointing, network partitioning, or anything of that sort is taken care of by DynamoDB streams. Now, what you're doing is you're just consuming the streams and replicating it to multiple regions. As you have it in any case, like if you have a single region, it is just going to your restore table and restoring it in point-in-time recoveries case. So you get exactly where you want to get to. Similarly, the concept of delayed replicas, like doing a restore, is a long process. So if you want to keep your replica, you want to keep the copy of the replica, which is 1 hour behind your main database. You can essentially, again, just write a stream processor, which processes all of your updates and builds a delayed replica. And the way you would build the delayed replica is you would just hold the updates and just wait until it's been an hour until you apply your delayed replica. So you can build that without paying a lot of money to the other companies that might want you to have these traditional solutions with licensing fees or for building your delayed replicas. That complex capability is just a stream processor in this case. Similarly, for cross-region replication, now you just must write a stream processor which processes the updates happening in your source region and replicates it to your destination region. So in this case, Portland and New York. Now, if you want to build materialized views, the example we talked about where you build a cache or an Elasticsearch cluster, again, a stream processor on top of the changelog and making sure your updates are just happening in real time, versus in traditional systems where you absorb the updates in a nightly fashion and update your analytics cluster or unit cache. It can happen in real time now. Now for a serverless architecture, you can just look at the primitive. And here also the primitive is the changelog, and you directly connect it to a Lambda function with your streams. For example, if you want to send a notification of an order which moved from confirmed state to ship state, now you can just write a small Lambda function which takes that input and sends out an email. So changelog sits as a common primitive. That's the building block that is common in all of these use cases. Now you can easily see that all these common problems, either we solve each one of these problems natively and provide solutions, or we can just expose this building blocks that lets developers innovate on top of this building block. So we thought, let's just expose this primitive as a stream of updates. And that's what DynamoDB streams is. And very specifically, DynamoDB stream is your transactional log inside of DynamoDB exposed to you in a Kinesis queue. So if you want to enable correctness in streams, how would you do it? How would we expose the right primitives to ensure that people can build the right applications? What are the key tenets that we require to be correct? So the first one is streams must be highly available. So consider streams like if you are building an application, you would start consuming these updates. So if streams is not highly available, you cannot build reliable applications on DynamoDB streams, right? So streams must be highly available so that you can build reliable applications. You can consume these updates in a reliable fashion. I can say this a little bit differently. I think basically if you're building a real-time system and the item and your update gets delayed and your updates are just gone for a while, that makes it difficult for you to say, I am making these updates in the right order or making these updates without an outage. So that's why real-time is important, and we need to be highly available to make the real-time system possible. And similarly, if you want to, as you're getting more and more throughput into these systems, you want to be able to support higher throughput. Regardless of what the rate is on the input side, you want this stream to automatically scale behind the scenes. Similarly, durability piece is also very important. I mean, you're building for correctness, a lost update inside your stream can have catastrophic impact for the rest of your application. So if you lost the delete message, for instance, your application downstream will have a lot of impact. And that's the kind of stuff you must do with a nightly reconciliation. But if you can make the stream delayed, and if you can get to a point where the updates are not missed, it means that people can build correct applications where they don't have to do a reconciliatory thread that's going on and make sure that things become consistent. And lastly, streams must be ordered and they must be deduplicated, meaning an entry that occurs and a change that occurs in a particular item and the second change that occurs after that must be exposed in a log in the exact same order that it transpired. Change only once. So let's take all of this, combine it into a voting system. If you must build something like a real-time voting application that gets the updates and votes are coming in, and you build something like this using two tables. One is the votes table, where as the votes are coming in, they're getting inserted. And then you have a vote aggregator table, which is processing the stream of updates and updating the count of votes for each candidate it's getting. So again, there would be requirements for a real-time voting application. And you want each person to be able to vote exactly once. And you cannot just let users vote multiple times. And to guarantee that, there must be concept of optimistic concurrency control distributed ways. What you use that for is build high throughput systems. Now, that exposes this. There are two different ways. One is conditional put, and the second is if not exists. So what you're trying to do here is you get one vote from this user. And in the specific case, what we will use is we will use put if not exists. So as the vote comes in, we will say, okay, accept this vote if it doesn't already exist. If it meets the that gets inserted to the database and gets exposed in the log corresponding to that. So here's what the stream record will look like. It has a bunch of information and it shows the new image, which is the actual image of the actual item that was inserted. And if you look at the old image, in this case, it's null. Now, let's say your application retried this case. So if, again, we'll do a put if not exists, and the put if not exists condition will be false, and the corresponding write will fail in this case. You can vote multiple times in some cases. Let's say it allows me to change my vote after the vote is done, meaning I can vote for a different candidate. So how do you make that happen in a system? So in this case, we're talking about the concept of conditional puts, which you can use. So essentially, the put if not exists that we had previously, if we have to change the put, if the vote is not equal to kill, which was the initial vote, and the vote was cabbage, so now it changes the cabbage to kill. So this particular voter, they changed their vote, and you can see the update has to go through. So if either the vote is inserted, we need to make sure that it is a change and it's not a duplicate. So that downstream, you don't end up counting it multiple times. So here you can see the change has been made. Here's how the stream record will look. Previously, the old image had the vote for cabbage, and now it has it for kale. And it's in the right order. So if you do a real-time aggregation on top of this update, let's the same use of the real-time voting, more votes flew in, and finally you want to count these. And you want to do it in real time, so you'll have a stream processor which is aggregating as the updates come in. So initially the vote was for cabbage, which would have been inserted once. And then the vote changes. So you can see the first two records there. What you will do in case of your stream processes is you will decrement one of the votes that cabbage got and insert a new one for kale. So your vote counting correctness is still maintained. You're not double counting, you're not doing anything that goes against the order itself. So the new candidate gets the vote while the old image is deleted, essentially. So the vote for cabbage is 3. If it's correctly 4, if it's currently 4, it'll get decremented by 1, and then you add 1 for kale. So the end image would be you'd have 2 votes for each. So we talked about scaling right now as DynamoDB as a table. So what you do is you provision your table, you create your table, and you set up provision throughput for it. And corresponding to that, we make sure that you have guarantees, whatever requirement you're provided with your provisioning. What we do is we partition your table into key spaces and distribute it across multiple storage nodes. Here you can see 3 partitions, 1, 2, and 3. So similarly for that, like for DynamoDB streams, what we do is we create a shard for your stream. So like DynamoDB tables has partitions, we have streams and streams have shards. So as a user, when you create a stream, you get a shard and then you write logic to process these shards. And in the order of the stream processes, you basically get all of these shards and process them into your Kinesis client library. So essentially, there is a one-to-one mapping between the partitions in the DynamoDB table and the shards that get exposed with your streams. And now the way internally it happens is a put that goes into Dynamo, it gets replicated. And once it's replicated physically to 2 different data centers, you'll get an acknowledgement that it's written. And then asynchronously, it is sent to Kinesis stream as a record that just shows up in your real-time system, which is being consumed. So now that we've gone through all the concept and one simple real-life example, let's go to a different one. Let's go through a use case that we had built out an event-driven application for on DynamoDB. So the use case here is that a startup needs a system to store and query data for its rental properties. There are a few requirements. Agents need to be able to change, add, remove property details. Customers need to be able to search for rental properties near them. So let's see what the performance requirements are. So you need to be cost efficient during the period of low utilization. Property updates tend to be infrequent, right? You're not going to update your property every single second. This is something that you do once or twice. Low latency, high performance reads. Property search traffic is extremely bursty. Like for me, for example, I always look at properties and most people actually go on Zillow or StreetEasy because now it's like a browsing feature. So it is extremely bursty, depending on the hour of the day, depending on what new properties and notifications are sent to customers that made them click on it. Fast geospatial queries are required because it's based on location type. You want location around where you live right now. It needs to be location-based, and it needs to scale easily. So going back to the concept, DynamoDB, again, is a NoSQL database, which will hold all of the items, in this case, the properties. And Elasticsearch is essentially a fully managed service that makes it easy to deploy, operate, and scale in-memory data store. So what you can use this for is essentially the geospatial queries that you need for the property data. So here's what the architecture would look like. Amazon DynamoDB is the system of record. And then you have an AWS Lambda, which essentially sends out any sort of event-driven notifications to Elasticache. And the geospatial search is done on it on the read cache with Elasticache. There are alternatives. For the system of record, you can obviously use RDS or Aurora reading cache. We also have DAX, which is DynamoDB Accelerator, and MemoryDB for Redis. Geospatial search is also available on DocumentDB, OpenSearch Service, and Geospatial Library. So let's look at the UI architecture itself. So you have a website, it goes through the AWS API gateway, and it uses AWS Lambda to look at the system of record or Elasticache, depending on whether it's cached or not. So then essentially, this is what the complete architecture looks like. So let's just look at like the property query flow here. So the property query flow goes from the web client and down to the Lambda function, which essentially retrieves the credentials and does the property query through Elasticache. And there's a Lambda function from DynamoDB streams table that basically populates the property cache. So what it's doing is it's doing the geospatial search via Elasticache and getting the properties relevant to that particular location there. And here's how the network architecture will look. Essentially, what you're looking at is the same that we had seen previously. So here's what the table schema will look like. There'll be a partition key, and then you're looking at the agency ID and the agent ID. There is sort key, which is state, city, address, which is essentially going to be where the property is. And here's what one particular item will look like. So on the Redis key, the storage data will look like this, where you have the property key, and then you have the property details. And the geospatial index, essentially looking at what the longitude and the latitude of the property is, which is going to be key for the search itself. So the geospatial search, you're going to enter the longitude and latitude value and a particular radius. For example, you want to look at 10-mile radius of this particular longitude and latitude. And you're going to retrieve the data related to that longitude and latitude. So that's how you get the geospatial search results. So that was the example that was a very good real life example for how exactly you can use data-driven architecture using Lambda, using DynamoDB, and streams, which we talked about a lot. So for the main takeaways, first thing, logs are a very powerful primitive. And how you design for correctness is really important. Checkpoint, ordering, deduplication, very simple, very fundamental concepts, but are very important for event-driven application. And log consumption semantics are very important. Like you have to think about what your use case is, and then how you consume the logs and how you're ordering them. That's everything that I had. Hopefully everyone found this very useful. Happy to take any questions if anyone might have any. Sure. I think the answer would be not satisfactory, but it really depends on your use case. Because what we have seen previously is DynamoDB has been the database of last resort, where customers see that their existing architecture doesn't scale beyond a certain point, whatever that point might be, and however they might have sharded their data, it just isn't working anymore. So they move to DynamoDB. So it really depends on what your queries are. As simple as you can make the queries, DynamoDB will scale very well. So it really depends on like what your use case is, how your data is set up, and how you're ready to transform it to be able to scale, get to the scale that you need to. No, I have not. I'm hopefully in the future I will, but no, I have not. Yes. Thank you so much, everyone. Hope you have a good rest of your conference.